If it switches off, please let me know. Okay? If it switches off, then give me a shout. Okay, so let's get started. We were previously working on transverse shear. We discussed that how the transverse shear is generated. We said that actually the genesis of transverse shear is the difference in the moments. If you have a bending moment diagram which is changing, so if you take a small portion of that bending moment diagram, the difference between the moments at two particular sections, that gives us shear force. And what I mean is, like for example, if we have a cantilever beam and it is subject to some loading, we draw bending moment diagram which looks like this. Now you take any section, any two sections, and you can see that the bending moment is changing between these two sections. So the shear force is actually the change in the moment dm by dx. So in other words, it is the change in the moment divided by this length L. That is your shear force. So this shear force, okay, so you might have M1 and M2 at two portions, at two sections, and you take the difference of them. From that difference you get shear force. Okay, and why do we get shear force? Because, for example, this is just to satisfy the equilibrium. So at one section you might have, sorry, this is facing down. So So what we are saying is that we have these two sections and this is the cross section. Okay, so in other words, we have got a beam which is subject to some loading, and this beam is divided into different sections. Okay, now at a particular section we take 2 points. Okay, we take 2 points 1 and 2. In between these 2 points the moment is changing, and so this is the moment profile at a particular cross section. Okay, so since this moment is changing, these forces, if you subtract them one force from the other, you will get some resultant force, and that resultant force is actually your shear. Okay, so if this was equal, then you will get zero shear. So that shear is a horizontal shear, okay, which you get from the difference of these forces, and these forces has come out from the moment profile. Okay, moment profile. What is a moment? Moment is force into lever arm. So you can draw your moment diagram like this along a cross section. Okay, so this is a moment profile, and it is made up of lots of loads which are varying. So at a particular point, so in other words, this variation is along the cross section. So we get a horizontal shear, a horizontal unbalanced force, which is called shear. And in the case of a beam is, for example, a structure is a 3D element. Okay, so a beam is the simplest structural component. So if you consider a beam, you can divide a beam into lots of small boxes, which I have shown over here. Okay, so these are all made up of these boxes. So we say that at a particular box, okay, at a particular box you will have force which goes like this, and at an adjacent box you will have force which runs like this, and the difference between them will give you a shear force. So in other words, if I draw one box which I have shown over here, I will have, because this is bigger, this moment is bigger than this one, so in order to balance it out, you must have a shear force which looks in this direction. Why? Because this force is less than this one. Do you understand my point? This force is less than, it should be in this direction. So the force which is at the top fiber, imagine I am taking a box and at the top fiber, I will have this minus that, and in order to satisfy equilibrium, I have to apply a force in this direction so that these two forces become equal. So that's why I have written this force, I have given the direction as shown over here. So this direction I have given you. Now, and this is, remembering that this is actually one box which I have shown in this specimen. So you have got shear force which is in this direction. In order to satisfy equilibrium, summation of fx must be equal to 0, so you will have another shear force which will be in this direction. And now these are horizontal. These horizontal they both cause a couple. So this couple must be counteracted by another force which is in this direction. Okay, and that is actually this. From there we get vertical shear force. So the vertical shear force you get from equilibrium satisfaction. So, and this is the same vertical shear force, and the shear force diagram when we draw, that is actually giving us the vertical shear force. Okay, so in other words, the horizontal shear force is equal to vertical shear force if we assume that this is a square box of very small magnitude. So the horizontal and vertical shears are equal. Now, let us solve this problem, and so we derived an equation which, so we'll use the same equation for solving this problem which we derived previously, and that was chi is equal to BQ by IB. So shear stress is equal to the shear at a section. This shear can be horizontal or vertical, okay, times the first moment area divided by the moment of inertia of a cross section divided by the width of the cross section. Okay, so that equation we have to use. Now, what is, let me rub it off and okay, so now look into this problem. We are given a beam which is subject to partially uniformly distributed load. This beam has got a T cross section. Now we are told that the flange of this T cross section is glued to the web of this T cross section. Okay, and so the flange and the web, they are glued to each other. So how much shear force this glue can take? So that's what we are told. So in other words, this cross section is made up of cardboards which are joined together at this point, which is a seam. Okay, so this is a seam, this junction. Okay, and we are asked to find out the shear stress at this point. Now, why are we interested in the shear stress? Because if you go to the market and you are buying a glue, and you are tasked to join these two cardboards with each other. So obviously in the market there are lots of glues available. Okay, glues of different strength. Okay, you have got glues which join two pages, and you have got special glues which join different wood planks. Okay, which glues should you take? So for that you have to find out the shear stress. How much shear stress the glue can take when you join two planks together with a glue. Okay, so it is the shear stress which is actually the governing factor in the case of glue. The glue will fail if you apply the shear stress. Okay, shear stress, and that shear stress is bigger than the capacity of the glue. Okay, so the glue capacity is a function of the shear force which is running into it. It's the shear force which failed the glue. So that's why you are asked to find out the shear stress at these 2 points. So this is just a simple, for example, two pieces of planks, you join them together, you are asked to join it together with a particular glue. But for that glue you have to determine the shear stress based on the loads, based on this load, how much shear stress you get at that particular point. And then you can go to the shop and you can say whether your glue must be bigger than the shear stress which you get from this scenario. Okay, so that's what the problem is. Now, as I told you, tau is equal to VQ by IB. Okay, this is the equation which we have, which we derive and will be using. Okay, so shear stress is equal to VQ by IB. Now V is the maximum shear at that point. So the maximum shear you have to determine. And how do you determine that? You draw the shear force diagram for this. And whatever is the maximum shear, you pick that one. Okay, so V you can easily find out from your maximum shear. Is that clear? Yes? Now, what is your I? I is the moment of inertia. So you have to find out the moment of inertia of this cross section. B is the width of the cross section. And Q is the first area moment. Now first area moment, how would you take? First area moment is equal to, Q is equal to A Y bar. So you have to see which area you are interested in. We are interested in this area. Okay? In this area. So we will be taking this area. Okay? The area of the flange. Why? Because this is the area we are interested in. The point of our interest is covering that area. The shear which is resisted by that area, okay, that is actually the shear which we can get from here. Okay, so that is actually the shear strength. So in other words, we have to find out the shear strength of this glue, and the shear strength is equal to VQ by IB. The V, I, B, they are straightforward. For a particular cross section, you just find out a generic term. Okay, they are general. They are true for all the cross sections. Okay, since the cross section is constant, so it is true for any cross section. The only difference lies in Q. Q is the first area moment, so you will see which area you are considering. Imagine if the glue you are applying over here, so then you would have been taking this area. Okay, but since you are applying your glue at the junction, so whatever is on the top, that area moment you will take. So in the case, so what do we need to find? We need to find, as you can see, the neutral axis. Okay, and from the neutral axis we will get our moment of inertia. Yes, so we will get from the neutral axis, then we will find out our y bar. So let us find out our y bar. Sorry, the neutral axis, y and a. Y bar, I'll tell you what it is. So how will we find out our y and a? Y neutral axis is equal to So what we are saying is that our y and a is equal to, you have done that, we are just trying, this is the centroid formula. Okay, the neutral axis formula, you are trying to find out the neutral axis. And how do we do that? You take a reference point and base corresponding to that point, you find out area moments. Okay, so divide it into pieces. Find the area moments divided by total area and you will get your neutral axis. So assuming that our neutral axis, assuming that this is our reference, so we can find out our area, which is for this one 0.15. These are all in millimeters. 0.15 into 0.03 area times y bar, which is 0.15, 150 plus 15 is 175, no 165. What is your 0.15 into y bar, which is 2.075 divided by the area, which is plus and from there we get our neutral axis equal to 120. Okay, so that is our neutral axis. Now, in other words, the neutral axis this is 120 millimeters. Now once this is done, then we can find out our moment of inertia. Moment of inertia about the neutral axis. So what we can do is we can find out I is equal to B h cubed by 12, so 150 30 cubed by 12 plus ADZ square. So area is 150 to 30, and this one is area dz square. So that 180 minus, sorry, 165 minus 120 whole square. That is what is that. Plus BHD by 12 for this one. Thirteen to 150 cubed by 12 plus 8, 115, 30. dz square. So its centroid would be 120 and that comes out to be that is our moment of inertia, I. So I is known, B 19.5, that's the maximum. B is 150. Now what we need is Q. So Q would be is equal to area, which is 150 into 30. That is 150 into 30. That is the area times y bar, which is 180. So 150 plus 30 minus 15, because it's half n minus 120. So what I have done is, as I told you, that we are interested in this area. Okay, that's the area which the shear is going to take. Okay, so this area times y bar. How do we find y bar? Y bar is from the centroid of this area under consideration, area of shear,